PyControl. We just walked by quickly.
Okay, so welcome to ETA number 03, so the fourth one in our counting. We have a Slack channel with now 13 people, last count, so please join if you're interested in discussing these things afterwards. Reach out to either Carmen, Andrew, or Stefan Breibisch if you want to give a talk yourself.
Or Frank.
Or me, in the worst case. And I think for next month, we have John queued up.
Yes.
So very much looking forward to that. It's a bit of a mystery to me what the title will be, but maybe we learn more about it later today. And for today, we have Andy talking about pyControl.
All right. Thank you. Today I'm going to talk about pyControl, which is a hardware and software system that we use to run our experiments in our lab. So outline of the talk, I'm going to give a brief intro, then I'm going to talk about the hardware, talk about the software, and then hopefully get to a live demo. The goals, hopefully by the end of the talk, you'll know in general how the system works, maybe be intrigued by some of the features, and kind of be thinking, maybe I could use pyControl to do X. I'm happy to chat with you about anything afterwards. But even if you don't end up using pyControl, I think there's a lot of cool technology with software and hardware that is in this system. So hopefully there can still be some crossover and we can share those things. You can get something out of it. And better yet, if you do decide to use pyControl or have existing tools that you've made, I'd love to talk to you about making it, integrating it with pyControl and making it compatible so you can have access to a lot of other neuroscience users. Because I know one of the tough parts about the stuff we make is it's hard to deploy and share the things after we made them. So a little background, this pyControl project was started back in 2014 by Thomas Ackham at Oxford. I started using it and contributing back in 2019. We converted the Karpova lab over to this system back then. There's a sizable community of, it's hard to estimate, but we think hundreds of users. Everything's 100% open source. So you're not locked into a vendor or anything, and you can always fix something if it breaks. You don't have to rely on an outside company to fix a software bug. You can do it yourself or improve upon the existing hardware and software. And then I think one of the things that separates this project from some other ones is it really does, I think, have some really great documentation and support. We have online support or online forum and some online documentation. In the Karpova lab, we've kind of taken advantage of this open source project and really used software, but expanded the hardware offerings by designing our own hardware. All of this is also open source. If you just search Karpova Lab GitHub or Karpova GitHub, it should pop up. And then just to kind of speak to the reliability of the system and kind of show some stats from last year. We've had 6 rigs up and running all year and have many hours of experiments, over 3 million trials, and delivered over 65 liters of delicious Kool-Aid. So yeah, pyControl system is the basic components of the system, roughly to scale. So you have here on the right the behavioral arena itself, and it has 4 modules in this case. If I flip around to the backside, you can see them better. So there's 3 nose poke devices and then an audio device hooked up to a speaker. these devices talk to this microcontroller, what's called the pyControl breakout, and then that talks to desktop computer that is running the pyControl GUI. So the way it breaks down is they use the main computer to set up and run and control and monitor your experiments and record the data. These devices that you can mix and match are used to sense the environment, and then you can use different actuators to, turn on lights or turn on sounds to affect the environment. And then in the middle is this microcontroller that's very low latency, and it's reading in sensor data from the rig and also sending out signals to actuate things. And all the while it's buffering data. Its top priority is tending to these devices, but then occasionally it will stream back data to the computer. This all happens very, very fast, and the end result is everything. We can record data at millisecond resolution. So when we talk about the pyControl project, this is what we're talking about: the software GUI that runs on the desktop, this pyControl framework that runs on the microcontroller, and then the different bits of hardware. So this architecture is flexible. It's very modular, and because the software is running on top of Python, you can easily swap out other elements of the system and upgrade as time progresses if you need to. So the GUI is cross-platform, so it'll run on Windows or Linux. You can swap out that sort of hardware. You can upgrade your microcontroller, and then you can mix and match the different devices to create the behavior rig that you want. Also, you're not just limited to these 6 ports for connecting the devices. You can add a port expander and add more devices that way. Additionally, on the back side of this, a couple of more connections for BNC cables if you just want to tap into a single signal instead of these 8-pin ports. Another benefit of this architecture is we can take advantage of the expensive but powerful computer that can process a lot of data and store it, but then below latency, small and affordable microcontrollers are easy to purchase, and you can easily scale up and still run multiple experiments at the same time, all from one computer. So a key aspect of how this system works is this connection between the devices and the pyControl breakout. It uses these RJ45 connectors. You're probably familiar. They're just Ethernet cables, essentially. Or not since they are. These cables are really nice. They're keyed, so you can't plug them in backwards. They click into place. You can get shielded versions or ones with twisted pairs to reduce the noise on the signal lines. The connectors have 8 wires, and so all you need to do when you're making a device is you adhere to this pyControl standard, the pinout. So each one of these ports has 5 volts, 12 volts, and ground on these lines. You also have access to 3 general purpose digital I/O, and with those you can communicate with I2C devices or UART devices. And then finally, remaining lines go through a transistor array, so you can use them to turn on some high current loads, such as like a solenoid or a motor. So the cool thing about this is as long as you adhere to this standard, whatever device you make is instantly compatible with any other user that has this pyControl breakout. So what kind of devices are available? You have this core pyControl breakout, which is kind of the brains behind everything. And then additionally, there's a bunch of other devices available, as you can see here. You can purchase these devices turnkey, ready to use if you like, from the OpenEFIS store or the LabMaker store. They sell kits and also individual devices, but of course, also it's all open source on GitHub, design files, bills of material, everything, so you can build it yourself or improve it. In the Carp of the lab, I've designed several devices, and I'll briefly go into a little more detail on some of them. Maybe some of the sensors and stuff will interest you. One of the first things I did is I redesigned the pyControl breakout to use a newer microcontroller that has slightly better performance. Importantly, it had more GPIO pins and more memory. So I was able to create a device that has 12 ports instead of 6 and performs a lot better. Also made a extendable and retractable lever, which is self-explanatory.
What do you use the lever for?
So the rats will hear a tone, and then levers will extend, and then they'll press down on the lever to make a choice, and then it'll retract. Yeah, it adds a element because it can retract. You can, convey that the choice is available or not, whether it's extended or retracted. Also made a haptic time of flight nose poke. So this uses this really cool time of flight sensor that can measure distance at millimeter resolution. And unlike other distance sensors that we'll use, it will measure like how much light is reflecting back as kind of a proxy for how close something is. This is actually measuring how long it takes for light to be sent out and bounce back. And so it's kind of, it doesn't matter what the surface is or how reflective the thing you're measuring is. What it allows us to do is, through software, change threshold for which we call like a good poke for the rat. So if we can make them go deeper or shallower, depending on how fast they're going. And we also added a vibration motor. So when the rat does successfully enter the nose poke, it does vibrate and give a little bit of haptic feedback. And this has improved the accuracy in which the rats do our tasks, because some of the expert rats will used to get really good at it, and they start going fast and get kind of lazy and not quite enter one of the nose pokes. So they thought that they chose that side, but our system wasn't registering it fully. So this was a solution to that. Also developed some syringe pumps. This latest version uses not that many components. It's pretty simple to put together. It uses some bent sheet metal, a couple of 3D printed parts, and some off-the-shelf motion components like linear bearings and stepper motor. It also has this circuit board that has limit switches built in, and these connectors that allow you to kind of daisy chain pumps together. So with the system, you can control up to 4 syringe pumps independently from this single motor controller. This is motor controller. Peter introduced me to these cool stepper driver ICs that are really cool. Before, you would have to kind of calculate your acceleration and velocity on your microcontroller and send those pulses to the stepper motor to drive it. Whereas this does all that computation on the chip itself. So you just give it a position and it will make all the acceleration and velocity changes for you. So a separate microcontroller with a color screen plugs into this, and so you can create whatever interface you'd like, and then you have access to 3 buttons and a rotary encoder with a button, so you can build whatever interface you'd like. It's can be useful. And then I designed it to be modular, so the controller just has to connect to these pumps, but to control the controller, you need to feed it power and give it some communication signals. So here I've made a pyControl connection module. So this gets its power and signaling from a pyControl port, but you could just as easily, I made a separate module that connects to USB-C and a barrel jack plug, so you can connect this motor controller directly to a desktop computer if you wanted to. Spent a lot of time also documenting, trying to document all these tools well. So again, you should check out Karpova Lab GitHub. There should be everything you need to replicate them. All right, now I'm going to talk about software. Starting with the desktop GUI, it's built upon these core Python libraries, PySerial for the serial communication going to the microcontroller, pyQt, it's a Python wrapper around Qt, which is a framework for building GUIs that run on all platforms, and they're native desktop GUIs. And then pyQt Graph is a nice plotting library that we use to see data live. And then the nice thing is, because this is all written in Python, you also have access to a bunch of other Python libraries. And we've taken advantage of that in Karpova Lab. For instance, this Notion client library, we can upload data to a Notion database, which makes it easy to browse different session summaries. There's also this Amazon library, so I can create a data browser, load it up to the cloud, and then people can access it as soon as the session is over and browse the data. And then there's this app called Telegram, which is it's a messaging app, just like WhatsApp, and it has a nice API. So everyone in our lab is in this group chat, and it's nice to be able to know when the rigs are being used and which animals are running. And yeah, pyControl can actually send you notifications. It's kind of fun. So now the software running on the microcontroller. So there's 2 parts to it. There's MicroPython and then the pyControl framework. MicroPython, basically 10 or so years ago, the capabilities of microcontrollers kind of crossed the threshold where they had enough memory and enough processing power where it was feasible to kind of squish down normal Python interpreter and actually get it to run on microcontrollers. One of the big advantages of this, which I'll get to in a second, is how fast it is to iterate, because you're just saving files onto the microcontroller. You're not having to recompile things over and over. The MicroPython project supports a bunch of different microcontrollers. I think in Jet, the Teensy is pretty popular, so you can get MicroPython to run on it. And these are the 2 microcontrollers that I've used before with pyControl. And then, just to give a little bit of comparison, I think a lot of people are probably familiar with Arduino. And so with Arduino, you download the integrated development environment, and it comes with a compiler, and you edit the code, you compile it, and then you have to upload it to the board. And this whole cycle, depending on how big your project is, it could take 10 seconds, 30 seconds, I don't know, tens of seconds. By contrast, MicroPython, it shows up as a disk drive on your computer, and the code, it's just normal Python files that you can open up in any text editor, make your changes, and click save, and it automatically, within 1 second, is running your updated code. So yeah, this is one of those things that, once you start using this MicroPython, it's sort of addictive, and it's a pain to go back to this slow iteration cycle. So some of the pros with MicroPython is just in general, Python's a more beginner-friendly language. It's very popular. I think it's taught at a lot of universities. There's a lot of tutorials and stuff online. Not that, there is for Arduino too, but it's easier language in general. If there is an error while your code is running, it will actually provide a trace back and show you exactly where the error happened. So that can be nice for debugging. Whereas with Arduino, if the compiler doesn't catch your error and then there's an error while the code is running, you have to kind of figure out what happened through other methods. But the big thing is this iteration speed it's very nice. Some of the cons is it is a little bit slower to start up, consumes a little more power, and the execution speed is going to be slower because you have this extra layer of the MicroPython interpreter in between your code and the hardware. But for our purposes, our microcontrollers are plugged in, so we don't care about it only starts up once, and we don't care about startup time. Power consumption isn't a problem. We're not building a portable device that runs on battery. Then execution speed, we found that it's plenty powerful enough for our needs because microcontrollers are getting insanely powerful. So this is a plot with different characteristics of these microcontrollers, and this is a logarithmic scale, and you can see it's just continuing to get very powerful. So
Andy, can you mention what the limitations of MicroPython are compared to regular Python? Like you talked about the strengths of Python being you could use just any library. Like how do you know what you can and can't do with MicroPython?
Right. So a lot of the essentials from the Python standard libraries, such as like math and some random functions, and it's like there's the slimmed down standard library that works. The MicroPython documentation is really good and explains exactly which parts of the standard library are included. But there are some, you can't like run NumPy or pandas on the microcontroller, but there are kind of slimmed down equivalents for each, or at least for NumPy, if you want to do fast numerical operations on the microcontroller. There's a lot of the libraries that you can use are focused more on like creating nice interfaces with different sensors. It's kind of hardware focused.
Have you run into any limitations that you've had to find like workarounds for, or you've been like, I really wish that it could do?
Yeah. So one of the nice things, which I'll get into in a little bit, is if there is a limitation, pyControl software, we have the capability of actually running Python code on the computer as well and communicating. So, for instance, in the demo, I'll have a script that's running NumPy on my laptop, and it will receive a message from the microcontroller that it once an update, the NumPy will run the calculation on a huge array, and then it'll send that back down. So you can kind of get the best of both worlds.
Can you mention the like integration with cameras? Do you know that?
Yeah, this company OpenMV has been doing a lot of work with kind of porting a lot of these machine learning like tracking models. Like this new one, I think it's going to come out later this year. It can do a lot of stuff at like 60 frames a second. Like I think object tracking and skeleton tracking, and I don't know. I'm not an expert, obviously. I'm talking to an expert that is. But yeah, I would check out OpenMV. They're doing some really cool stuff, and yeah, like on the edge tracking, I guess is what they call it.
But that would be the place to look for, like, if you just want access to your, like, to a camera that's on board and you want to grab frames from it.
Yes. For us, we have the camera, separately, connected to the desktop computer. And if you are using OpenCV or something to process those frames, you can send information like a tracking position back down to the microcontroller if you want. Because
I guess I was thinking of a like, because you have a picture there, it looks like, of a camera on a microcontroller. So I was thinking about the camera on the microcontroller and wanting to have direct communication there, which could be super cool.
Yeah, that's I think these are getting pretty good, and that could definitely be a possibility.
We're using one of these OpenNV cams because it was laying around, so it's like overkill for this thing that we're using it for, but it's doing some like object tracking location, and then just like sending a TTL pulse out to a controller when we want it to, like, say it registered an object. So they're pretty easy to use.
And they've got, I haven't played with them in a while, but they've got basic like blob detection and color detection, but they also, I think you can load like body position tracking models and stuff, and it'll do the inference on the board at like 60 frames per second. It's pretty wild. Let's see. How am I doing on time? I got 15 minutes. Sorry, I might speed through this, but so what's actually running on the pyControl microcontroller? A lot of this the code is a bunch of utility functions. Sorry, the main goal is to make it easy for the experimenter to describe their experiment and write the task logic to run that experiment. And so to do that, there's a lot of this utility code that supports making it easier to write your task code. But as a user, you won't have to touch this. As an engineer, if you do build a device, it might be nice to write some driver code that would also live on the microcontroller. And so this, for instance, is a audio playing device that communicates over UART. And this is the driver file that kind of creates the API. So then when the user actually is writing their task code, they have a nice simple interface of instantiating the object and then saying play, stop, set volume. They don't have to do all this bit masking and sending chunks of data. So ultimately, this process should be easy for the experimenter to write the task in format of state machine, which I might have to go through it fast, but ultimately you would, in a text editor, write your task logic, and then save that onto microcontroller. And then using the GUI, you would run, start the experiment, and all the task logic is running on the microcontroller, but then data is getting sent and recorded on the computer. So just probably going to speed through this because I do want to get to the demo. I apologize, but this was probably going to be bad anyway. The documentation is much, much better. I encourage you to look at the pyControl documentation. But basically, the system kind of forces you to write your tasks in the form of a state machine. And this is makes the code easy to maintain and kind of reason about. Basically, some of the basics is you can only have one state at a given time, and the whole job of the state machine is just to process events as they come through. So you have a current state, and then you're constantly just processing events as they happen through that state. You can switch between states, but again, you're only in one state at a given time. So here's what a basic task the experimenter might write would look like. This is the same file, but I've split it up into two windows so you can see everything. So at the top, you define what hardware you're going to use, and then you can label, as you instantiate these pieces of hardware, you can give names to the different events that can occur from this hardware. And so here, and then you would define what states you have, and each state has its own function with code for how you would process these events. So, and there's different type of events. You can have external events that come from the hardware, or you could have timers that are also events. So you can set a timer, and when it expires, it will also create an event. So I'm going to quickly go through this. Here we define a poking and pressing state, and we said this poking state is going to be the initial state. Also defined all the events that could happen, and then there's two special events that I haven't mentioned yet, called an entry and exit event, that will be sent out whenever a state changes. So here, we'll start this session. You immediately start in the poking state. Because you entered the current state, an entry event gets sent. This entry event is processed here. Then, say you enter the nose poke. Because this event is processed through this function, we can run this code. I apologize. I'm probably going to fast forward through this just so we could get to the demo. But basically, we're constantly receiving events and then processing them through these different states. And it's a nice way to organize the code. If we're in this pressing state and we get a nose in event, we can safely ignore it because it's not in this processing function definition. So yeah, that was a terrible job. I'm sorry. I encourage you to look at the documentation. It's really good.
Is there anything in your code to make sure that in your pyControl code to make it know that or tell that you've actually not left any holes, right? That there's not some state event pair that you're not handling, or you as the programmer are responsible for everything.
You're responsible for that.
Okay.
So now I will attempt a live demo. I think the Zoom people can see this, maybe. Okay. So I have a dummy setup with some nose pokes, syringe pumps, a speaker, and a lever, and a wheel. And now I will do some demo stuff. So this was that task that I was just, so yeah, this is pyControl over here on the left. And then over here on the right, I have the task code for that task that I was very poorly describing moments ago. So I'm going to, I just connected to the microcontroller over here. And now I'm going to upload the task and run the task. And so you can see down here, we have a live graph of which state we're in. And below is a live graph of the events. So you can see as I do stuff, the events show up live right there. For this task, I think it has me, the idea is I will poke 5 times into the nose poke, and then the lever will extend. And each time I go in, this light turns on. So now that the lever is extended, I have changed into the pressing state. And now I can poke in here. The events still get logged with a timestamp, millisecond resolution, but we can safely, right now we're using this function as the current state, so we can safely ignore this stuff. I'll press down and do audio. If I hold for long enough, the tone will change, signifying that I've held long enough, and then it will change back to the poking state. You can zoom in on this. You can also pause things. It's very capable.
Is that variable just like just a kind of a debugging statement?
Yeah, so at the start of each session, it says all of these variables that you defined. It gives you what they were at the beginning of the session, and then at the end, it also repeats what you ended up with. Because I'll show now a little more complex text, and I'll show how you can use the variables. Actually, I'll show that now. So you have this. You can pause, zoom in. That's cool. But then also you have these controls that this dialog automatically gets made and populated with whatever variables you defined. So I can change it to, I want 10 pokes. And now that is also logged with the timestamp with new variables. And now I only care about holding for 500 milliseconds. So now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's much quicker. You can even simulate events. So now I'm going to trigger it from my computer. So that's nice for debugging. And you'll notice there is a distinction in the log that this was a user knows event versus when I do it with my finger, it's a hardware input event. And also you can add notes like this was a cool thing I saw, and then that can get logged to the data as well. I'm going to now do a more complex task. So I've added a syringe pump. See if I can make this a little bigger. And a running wheel to the mix. So here now, you can set, so now the running wheel automatically added this analog plot, so I can see live data of the analog signal, which is nice. And you can set in this case, a velocity threshold. And so now this task, it's the same task as before, but now I can spin the wheel, but it will pump the syringe at the end of the trial, and I can spin the wheel, and if I keep spinning for a certain amount of time, it will give me a bonus. And so we can see here, I crossed that threshold, which was 500, and immediately this wheel spinning event was emitted, which triggered us to change states to the wheeling state. And then once I was in this state for 4 seconds, the ran enough event, which I defined down here, was emitted, which then sent us into the bonus state where we could dispense reward. So all this makes it really nice for, the data is organized well and at millisecond resolution. I can show you, oops. But yeah, the data gets saved as a TSV file. Whoops. You have a bunch of different information about you get the point. It's a TSV file, very easy to parse, which is nice. And then the analog data there's a separate time series and value series saved as a NumPy array. Then quickly, some cool features. Talking about the API, here I'm going to define an API class, and then I now have this separate script called the demo API that is running on my laptop. And so this has an array of 1 million elements. And so this would be unreasonable to try and manipulate this array on the microcontroller itself. But now I can do a task. And here you can see it got information from this script. It did a large summary, it summed all the elements in this array and then took the average and mean of like a random slice of this large array. So that's another poor demonstration, but a poor demonstration of how you can run more computationally heavy tasks on the laptop or on the desktop while still communicating information back and forth between. And then another cool thing is you can, especially if you have a lot of variables, this can get kind of unwieldy. You can make custom controls. And so now when I upload this, oops. Now we have a custom control interface. So if I start session, I can change the threshold. So this is a nice way to create interfaces and update select live. I can simulate with buttons. And you can make more complex interfaces. You can also edit it. I'm sorry, I timed this very poorly, not in demoing everything. But the user will usually, this is the run task tab, and the user will usually develop the task with this, but to actually run an experiment, I'll go straight to this. You have this interface, and so you can have your plot over here to the side. And if you have multiple animals running at the same time, this can be useful. So for instance, I'll finish here. Sorry, I did this time poorly. So now, the pyControl GUI is designed to run experiments in parallel. So I can start, I've got 4 of these pyControl boards hooked up, and I can run them all at the same time. And you can still adjust things like normal. Yeah, I think we're out of time. Sorry, I ran over. Thank you. Hopefully, yeah, I tried to cover too much, I think, but there's a lot of stuff here. If you're interested, yeah, I'm happy to chat about it with you. I think it can do some cool stuff. And thank you for your time. Yeah, I don't know if we get kicked out or anything, but yeah, any questions?
What's the best way to get started?
To get started, yeah, there's a great documentation. If you just search pyControl on Google, it should be the first result. I've got some extra boards if you want to play with them. You can also order different modules from the OpenEVIS store, like I mentioned. But yeah, there's information here on, yeah, much better than what I just did. But like how to program tasks, what the built-in functions are. There's like time state transitions. There's a bunch of random functions that you can use. You can shuffle things. Yeah, I would suggest taking a look at pyControl documentation. Do you have a question, Kristen?
Yeah, you showed an example where you did some of the computation on your laptop, and I don't have a sense for when you want to do that versus you can do it on the microcontroller. Like, is a million a big number, for instance?
I think so. So for us, we use it because we want to set certain variables in the task depending on their choice history. And so we're actually keeping track of their entire choice history, which is like 400 or 4,000 choices. And then we run like a predictive model stuff on the laptop that we, yeah, it would take too long if we tried to do it on the microcontroller. So that's how we do it. We also use this for, the Telegram notifications and stuff like that. If the syringe pump reaches its limit, we want to stop the session automatically and then send a message on Telegram, and the microcontroller cannot connect to the internet. So yeah, that's another.
But like, did you try it on so this algorithm for predicting, like, did you try it on the microcontroller and it was too slow, or you just have a sense of like, this is too complicated to run on the microcontroller? Because I don't have that sense.
Yeah, I think we didn't try it on the microcontroller, but had a sense that it would have been too slow. It probably would have been, I mean, slow here is like hundreds of milliseconds instead of on the computer it would take microseconds.
I guess what's the slowdown? What do you think the slowdown is between the microcontroller? I know you have an exponential curve of increase, so that won't be relevant tomorrow, but today, what's the slowdown?
Like between compiled C code versus MicroPython.
No, between a microcontroller and the stuff you're running on your laptop in whatever language it's running on your laptop.
I don't know.
The clock speed is much higher on
the
laptop. Yes.
The clock speed is probably it's 200 megahertz versus 4 gigahertz. Oops.
Okay.
Yeah.
So like a factor of 10.
Yeah.
You probably also run this problem that MicroPython doesn't have all the libraries, while you have access to all the libraries on your computer.
Right,
so
right.
Run much more elaborate
Exactly.
models.
Yeah. So like, if you wanted to use scikit-learn or something to run some complicated statistical things in parallel, you could use that library on your laptop because that doesn't exist on MicroPython.
Andy?
Yeah.
So we have to wrap up. There's another.
Yeah, sorry.
You want to walk over? Yeah.
How difficult is it to like integrate if you have like equipment that you wouldn't plug into like the pyControl breakup or like a USB camera or something you wouldn't necessarily like plug in to like integrate into like your experiment script? Can you just like use Python as an interface to say,
Yeah, you just kind of write
autopull in
like a
stuff from-
driver file,
Okay.
and you can just like import that.
Okay.
Yeah, that's the nice thing is that since everything's Python, you're not switching between like LabVIEW and MATLAB.
Yeah,
and it's kind of.
Okay.
I texted you, but I figured you were not taking text.
So you need help with multiple
Sorry,
projects?
yeah.
So anything Andy does, I understand why.
You said there's 12 volt and 5 volt power. Should be
Thanks, Andy.
like from each port. What's like power and power that
You can supply supplemental if you need to.
you
Also,
have for like stepper motors and stuff, or are you powering them through?
I'm powering the stepper motors through the port itself.
Okay.
But yeah, you can draw like I think like 300, 400 milliamps or something like that. It's the limitation is actually the Ethernet cable.
Yeah.
Like there's suggestions for like how much current you want to do that.
Gotcha.
Were you doing a full-on demo, Andy?
Tried to. It was sort of just I leave enough to didn't leave enough time. Yeah.
Naveed, you're clearly participating in this meeting with great interest.
Is that a syringe pump or something?
Yes.
Looks like it.
I just bought one. I probably should have asked you guys.
Yeah.
Anyway, money has been spent.
What's the primary application of your syringe pump?
Delivering Kool-Aid to rats.
This is an Allah thing?
Mm-hmm.
Yeah.
Fully integrated with
What do you use? Well, I was considering this flow cell assay.
Can you log out of this
you know,
Zoom
like
meeting?
fluid to
Even though
generate
David, poor guy,
flow
clearly
on
is
the beads
listening with
as a
rapt
test.
interest.